Hello, everyone. My name is Slava Dubeyko, and my question for today, can file systems survive in data-centric world? So who am I, and why I'm asking this strange question? So I am a Linux kernel developer, file system guy. I design SSDFS file system. I actively contributing in CFFS kernel client. I maintainer HFS, HFS Plus, file system kernel driver, Linux kernel driver. I contributed in LFS2, so I'm file system guy. And this question is really important for me because it's my future. But from another point of view, it's possible to think, what is a strange question? Because if we are not talking about data, we imply file system. If we are talking about file system, we imply data, and especially for data-centric world. But the problem here is that technological landscape is actively changing, new technologies are coming, so it's not so easy question right now. Can file system survive or not? So, and we will see in the whole of this talk that it's a pretty difficult question. So first of all, let's refresh. What is file system? What's the point of file system? So file system, it's robust fundamental technology, but how it's built? First of all, we have three fundamental types of memory. It's persistent memory, it's volatile memory, and we have register and CPU core. We have L-cache. So usually we we assume that persistent memory is slow, volatile memory is faster, and the most faster is registers in CPU. But we have something like 100 registers, and we have small cache, so it's already possible to see some interesting problem here. But we keep our executable code and user data in persistent memory. Usually it's huge. But if we would like to execute some code, if we would like to process some data, we need to run start application. And usually we create something like image of the process in the volatile memory. We need to prefetch executable code into image of the process, and then we can open file, prefetch data again in volatile memory. Usually volatile memory contains only something like sleeping processes. And if you would like to run something, process has time slices, so we go into instruction cache, instructions go in instruction cache, data go in data cache. And finally, magic has happened in registers because we place some machine instruction in registers, arithmetic logical unit do magic of calculation for us. So finally, storage device, it's persistent memory, and storage device hide from us complexity of persistent media management. It's a pretty complex problem. And storage device introduce physical sector concepts, and we can access data or store data without something like knowing how it's complex the process of storing data in persistent memory. So file system responsibility to hide complexity of metadata management. And finally, file system provides for us file concept. We can easily access data, store data. Also, file system introduced for us namespace concept, permissions, reliability, snapshots, multiple really nice, really useful stuff. But our assumptions that, for example, we have slow persistent memory and we need to copy data, executable code into volatile memory, so it's something like fundamental basis of the whole paradigm. But where do we now? So we're living in the world of big data that was created by phenomenon of social networks, cloud computing. We have smartphones, we have sensors that generate a lot of data. We need to store this data somehow. We need to access this data. We need to process this data. If you're talking about artificial intelligence and machine learning, so we need to train our models. We need to access a lot of data. So this is something like already some problem because we would like to operate by huge amount of data. And finally, even right now, file system cannot serve or cannot satisfy this request. Even storage devices near some technological limits because we would like to process more and more data. And this is a big problem. So is it something like temporary problem or it's something like really fundamental issue? So what's next? What's in the future? So I can something like say multiple smart words. Artificial general intelligence, quantum computing, quantum AI, neuromorphic processor, CXL, blah, 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 disaggregated architecture, and so on. It's really smart words, smart technologies. And I can combine currently these smart technologies in any way. For example, let's imagine that artificial intelligence will work on basis of quantum computing by using neuromorphic processing in data-centric computing, in the persistent memory. But where file system in this equation? I don't see file system. And if we return to the current reality, so people believe that file system introduce overhead. Because, for example, again, we need to copy executable data, we need to copy executable code, we need to copy data into volatile memory because it's an inevitable step. But let's imagine that we are talking not about hard drives, not about SSDs. Let's imagine that we take MRAM. MRAM is persistent, MRAM is with good endurance, it's fast, it's comparable with DRAM. And let's imagine that we have a huge amount of this memory, terabytes, exabytes, I don't know. So what's the point to make this copy operation? It doesn't make sense. It's redundant operation because what's the point? This copy operation doesn't make sense because we can keep data in persistent memory, we can operate in persistent memory. So this is the point. Okay, so what's the possible solutions? Some guys go in user space and place file system functionality in user space. Some guys trying to place file system inside of storage device. Some guys trying to split file system functionality in multiple layers and place something in firmware, something in user space, in kernel. But can it solve fundamental problem? So is it something like, so file system is important, but is it file system the main problem overhead? So for example, maybe file system is a small puzzle of the whole problem, because if you something like considering the computing paradigm itself, so what we have in current hardware stack, so we have memory wall problem, because we are using something like L-cache, we are using multiple cores, we have cache coherence problem, we move data a lot. So any application, something like 60% of application activity is data movement. If you're talking about network interfaces, it's moving. Moving data a lot, but what does it mean moving? Moving is not, it means that we something like consume a lot of power. We something like generate a lot of heat. So power consumption, it's something like one of the big problems. And this problem and our hardware stack makes artificial intelligence unaffordable. So we need to build nuclear station to feed artificial intelligence stuff, because human brain consumes 20 watts of power. And we are creative human beings. We can something like make a lot of stuff, interesting stuff. But artificial intelligence requires gigabytes of energy to do some stupid stuff that we can do in easy ways. So this is a big problem. And if we return to the question, can file systems survive in the future? So it's possible to answer in three possible ways. Yes, maybe no. So if I believe that yes, file system can survive, so I possibly, and I try to do some tricks, for example, in my file system. So we can use hardware acceleration. And it can help something like accelerate metadata operation, maybe some operation with user data. It's one of the possible ways. Another way, for example, maybe because potentially we maybe need to use something like completely different paradigm of data processing, data access, but for example, file system can still work maybe in storage device, on firmware level, somewhere else, we still will use file system, but not as we're doing right now, because potentially file system stack will be not necessary. And answer no, because potentially we can use completely different representation of data, completely different principles of storing data, accessing data, and so on. It's also one of the possible ways. But let's considering what's the future, or even not future, what current state of the art, what's the current trends. So current trends, amount of available data is growing because phenomenon of artificial intelligence, something like triggered in 2016 because we had enough data to train our models. And our data is growing because we generate a lot of data. It's the first trend. Second trend that, for example, capacity of volatile memory is growing. Capacity of persistent memory is growing. So today, 1 terabyte of DRAM in one server system, it's something like not big deal. But if it's something like taking a look at 1990s, so it's 32 megabytes of DRAM, 300 megabytes of persistent memory, so and it's significant growing of hardware capabilities, and this is something like second trend, that capacity is growing. And third trend that every new technologies generate a lot of data. So it's another big source of our troubles. So if we generate a lot of data, we need to store this data, we need to access this data, we need to process this data. And if we haven't something like good way to manage these requests, so what can we do? And again, return to future. So for example, if we are talking about these fancy new technologies, so quantum computing, neuromorphic computing. So quantum computing potentially needs completely different representation of data. Maybe potentially processing unit will also and store data, because the ideal case, if you can store and process data in the form of lights, in the form of photons. So it's great, but file system cannot provide such way to operate by lights or something. Neuromorphic computing possibly will keep knowledge or keep data even in neural networks itself. So what's the point to store data maybe in persistent memory? But again, who knows? And the problem with quantum computing is that it's micro quantum computing that working on macroscopic level. But for example, memory cell, it's something like so quantum microscopic, memory cell macroscopic objects. So it's not so easy to operate in memory cell on quantum computing principles. So artificial intelligence possibly would like to access data in our own way, store data our own way. So again, we are file system here. Cognitive computing maybe can use file system, but again, it's too expensive from my point of view. So again, potentially it could be something like another representation. If you're talking about edge computing, so potentially we can keep data in sensors, do some information analysis there, and we don't need to store data into cloud computing or somewhere else. Okay, let's return to file system again. Which concepts build file system? It's file, storage device, process, namespace, permission, POSIX, programming model. So, as I mentioned already, storage device hides complexity of persistent media management. And storage device builds physical sectors concept. It's a really important concept. Finally, file system can use this concept to implement file concept. And file concept is something like file. It's infinitely growing byte stream. And file system know where is every block is located. So process, it's something like container that keeps knowledge about how to access data, how to store data, and so we can finally open file, close file, read, write, and so on. Namespace also pretty important, pretty useful concept, because we are human, we would like to access data by names, And namespace create for us this convenient way to access data by names. So, and permissions, of course, we would like to manage rights to access some data or doesn't provide access to somebody that hasn't proper permissions. POSIX model declare for us API, how we can access files. We need to open, close, read, write, and so on. And programming model based on abstract machine concept that define for us how we can define variables, we can something like define loops, everything that provides a way to process data in something like automated way. So it's something like building blocks of file system. And can these building blocks work for future technologies? Probably no, because storage device, it's something like pretty complicated system, but finally again, as I mentioned, quantum computing needs our own representation. And finally, okay, so potentially or not potentially, so in the future, how data looks like. So probably it will be something like unstructured data, heterogeneous data, so probably it will be disaggregated architecture, so it will be distributed data, probably it will be not big data, but maybe huge data set and so on. So it's something like really hard to manage in concept that file system is built. So it's possible to discuss this, but finally, anyway, because everybody knows that file system introduces overhead, so it should be some problem somewhere, and possibly problem in these concepts. And can we completely get rid of file system? No, we cannot. Because first of all, we have multiple legacy file systems. We keep data already in file systems. So and as minimum, we need to something like provide access to this data that we already have in file systems. So finally, again, it's mature, it's robust technology, and people would like to use, and maybe it's not so easy to forget about this. Also important point that anyway, even it doesn't matter where we keep data and how, we need to provide reliable way. And any technology, quantum computing, something like could provide some errors, we need to make some error corrections and so on. So we need to guarantee reliability of data. And for example, if some metadata will be used, they can be corrupted, we need to use some way that file system is doing. And again, namespaces, permissions, multi-user model. It's important stuff that finally we need to provide too. So let's return to the analysis of concepts. So first point, first responsibility of file system always was to be mediator between slow persistent memory and fast CPU. But now it's not the point, because again, if we take byte addressable, fast, persistent memory with good endurance, so in this case, it doesn't work right now. And finally, if we're considering that we have really good byte addressable persistent memory, we can place this memory in CPU, we can place this memory on the layer of volatile memory, do something like hybrid memory. We can place, again, storage device. And finally, again, we can place computation on every layer. We can place computation in, of course, CPU. We can place computation in memory. We have computation in memory approach. We can place computation in storage device. We have computation in storage device. So we already have something, smart SSD, for example, and there is some approaches to do computation in memory. And of course, we are using CPU. But where is file system here? Because file system expects that, for example, we have storage device that cannot do computation, and we have computation in CPU. And everything is executed by CPU stuff. So, but what's the point? So again, it's this point doesn't work anymore. So storage device, pretty useful device with good concept. This device hides complexity of management of persistent media and create for us physical sectors. But from another point of view, storage device has limited capacity. 20 terabytes, I don't know, 1 terabyte, 2 terabyte. What does it mean? It means that we can create, okay, we can use LVM, but forget about LVM. So finally, we introduces boundaries between data, because if we are talking about big data, we need to distribute our data amongst multiple devices. Even if we are talking about one device and about physical sector. Physical sector, for example, 4 kilobyte. Even now we are talking about 16 kilobyte and so on. So it's the problem here is that our data can be split between multiple something like physical sectors. And it creates some boundaries. And if you are considering disaggregated architecture, CXL memory, for example, distributed huge neural networks, so potentially, let's imagine big shared memory, fast. CXL, not fast, but fast. So we can place our data there, and we can process data there. It's slightly convenient, but the problem here is that potentially we don't need storage device. Maybe we can consider architecture without storage device itself. So, and if we considering finally, or not finally, if we considering file concept, should or could this concept survive? Because file, it's something like byte stream. And file system never know what is inside of this file, what this byte stream means. File system never operates and never has knowledge about what inside of this file because it's application responsibility. But if we would like to do some processing, it means that we need to deliver data into CPU, and then we know what does it mean of this byte stream. So it's not so interesting. And finally, even potentially it's possible to use files for artificial intelligence because it's possible to imagine that we can use small files. But it's expensive because it's metadata overhead. And finally, small files, for example, 64-byte files, it means that we need to allocate 4K logical block in worst case for these 64 bytes. So it's expensive, so it's not so good point. And potentially, for example, another point that current state of the art of file system cannot provide is relations among data. Maximum that we can provide is something like folders, hierarchy, nothing more. But if we need something like more complex relations among the data, and if it's something like small data, so it means that file system cannot provide this. And potentially, let's consider that, for example, we have some smart memory, persistent memory. We can store data in the form of blobs, keep some metadata with these blobs. This metadata can track something like relations amongst these blobs. And finally, we can add something like some neural network of names and create connections among these names and these blobs. And finally, it's something like, it's possible to think about this like some neural network or something. But finally, it's something like different way, a more flexible way. It's not file, but it looks like file. And return to namespace concept. So again, namespace is important, but it's something like, again, it's limited. And let's imagine that, for example, we can have this data as data instances. And finally, data instances can be grouped or something like classified in some classes or data types, and then finally we can build some dictionary on the basis of these data instances, and finally Notion can represent like some class of data or some type of data. And finally, we can take chronology also in the equation, because finally, when we store some data, we store data in some chronological order, and we can take into account this chronology. And finally, we can build something like something like information reality, when our data instances can be generalized to some notions, and notions can be ordered in some chronology, something like this. So the point here is that we can improve what file system can provide. For example, we can make this technique, this methodology concept much better, for example. Why not? And permission model. Okay, so I simply started to think, okay, let's imagine that we would like to do permission model in some distributed manner. Because, for example, what does it mean, permission? It means that, for example, we would like to provide some information to one guy, and we would like not provide some information to another guy. So let's imagine, let's consider allegory of image. So, for example, if I make blurred image, I cannot see what's inside of this image. I can see something, but it's not image, it's not information. And potentially, let's imagine that our object will be active. An active object can something like track permissions or my credentials and something like give me information, access to information on the basis of this permission. If I haven't permission, my credentials is not good enough. So finally, I will see something like blurred image, something like some information, but not actually what finally in this object. And this active object can something like manage how different users can access different data, something like this. And finally, programming model. This is an important point, because finally, if you would like to use some new way of accessing or processing data, we need to consider some modification of programming model. And the important point here is that finally, okay, what is the point of computing in storage? What is the point of computing in memory? The point to process data near the place where we keep data. And it means that computation offloading of computation can be something like building block of new paradigm, because it's possible to imagine that, for example, we still keep data in persistent memory. And finally, we can something like have there also computation power. And finally, persistent memory keep real particular instances of data. But finally, we can generalize this data to some data type group with data into some class. And finally, we can use generalized algorithms. It means that when, for example, we will write our application, our code, finally we don't need to something like define some instances. We can something like define something like generalized code. For example, C++ has templates, Rust has something like how it's got traits. So it's something like functionality for types. And finally, we can something like use this for executing our computation. It means that finally, when we run this application, so this application simply can say that I would like to process data of some type, and something like deliver this offload to storage device, for example. And storage device will find what something like data instance exists for this type, and finally, computation will happen in storage device for this particular data instances. So finally, it's possible to imagine that, for example, persistent memory can do some particular computation data processing, something like volatile memory or other memory can do something like keep algorithms, like something like knowledge how we can process some data types, and this computation can be delivered to persistent memory. And for example, CPU or processing unit can simply have knowledge about how to something like combine several algorithms into something useful, like application. Because what is application? Application is something like sequence of algorithms, nothing more. So it's something like possible modification of programming model. And if we try to combine this into some potential picture. So if we consider in current state of the art, so we have raw data in the form of physical sectors, we have something like file like knowledge about where this physical sector is located, and we can extract, combine. So we have metadata around file, inodes, the entries, and any file system has a lot of metadata. I love metadata, but finally it's overhead. Then we have some functionality because we have API, and that, for example, we have EFS in Linux kernel. And finally, we have interface like POSIX that define interface, how we can open file, read, write, and so on. And let's consider some analogy here. For example, again, we have raw data, and raw data can be something like generated by sensors, and sensors can do some processing or do some machine learning stuff to detect something like what this data type we have finally, and maybe some active objects can be created because potentially, let's imagine that we have some processing unit that can collaborate with machine learning on level of persistent memory, and then something like take proper objects, combine with, then finally we could have something like hardware acceleration in the form of, I don't know, neural processing units that can combine with active objects into some networks, and finally some disaggregated thinking memory can do some smart stuff for us, and finally cognitive computing can be something like the way to operate by data, and this data can be something like finally consumed by artificial intelligence, some other agent, and so on. In this case, we, for example, can operate on the basis of some knowledge, even we can something like use some natural language on cognitive computing level, and finally the really smart stuff could happen in this whole stack. It's some vision, it's some answer, but again, it's something like maybe you don't like this answers and so on, it depends. But we definitely have problems. And we have overhead in file system, and we have some problems, and it's possible to find or to see multiple possible solutions. But even if I will use some hardware acceleration, even if I will use computation offload, can I solve memory wall problem? Maybe yes, maybe not. And currently, guys would like to use Excel, try to revive something like shared memory paradigm, and so on. So it's possible to talk about this a lot. And I thought about this maybe 10 years, and something like this summary of what I thought about how we can solve this problem, because potentially we can, for example, leave only VFS and forget about all particular file system, forget about XFS, X4, my file system, use only VFS that will operate in persistent, byte addressable, fast, non-volatile memory, and so on. But from my point of view, it's possible. From another point of view, it's not so easy, because there are a lot of problems here. And again, to save VFS, somebody will try to save current file system stack, okay. But again, if you're considering quantum computing, it will not work. If you're considering neuromorphic computing, probably it also will not work. So, and goal of my talk, not give answers, but raise questions and try to think about, let's not polish only. Let's try to change the whole paradigm, because finally, I think it's possible. We simply need to make some steps ahead of this. So I think I forgot maybe half of the smart sentences that I prepared. But I think anyway, it was useful, I hope, and it's something like answers to some questions. And I think I need to make some disclaimer. I'm working for IBM, but it's my personal opinion. It's not IBM position at all. So, okay, so I think it's all that I would like to share today. I'm open for, thank you for attendance. I'm open for questions and maybe discussion. So let's do this.
let's just say like it's a customer or like just like a user who's not as technical, then but is using your software.
So the question, what is the best way of user interact with future systems?
Yes.
Okay, we are human kind, and we would like to talk with this stuff. I remember even 20 years ago, my colleague something like said, I'm talking with the computer because I'm trying to write code and trying to talk to him and so on. I think it's one of the useful way. And finally, why not? We have right now large language model. You can talk with this stuff, and this stuff can do something for you. So I think it's one of the probably the most natural way to interact with the whole stack. You simply can, maybe you would like not to talk, but you would like to write sentence. And finally, what is sentence? Is it something like the set of keywords? And what is set of keywords? It's something like your definition of request. And why not place this set of keywords as a request to the system? And why not store data? Because, okay, let's imagine that we would like to store data into our storage device in our file system. And finally, let's imagine that our file system, our storage device, can analyze these patterns. What is the knowledge for us? It's repeatability of patterns. And finally, why our system cannot detect this repeatability. And finally, generalize to some knowledge, to some notions. And you provide to the system the same set of notions. And finally, system can simply compare. You provided me this set of keywords, and I have this bunch of keywords with some relations. And finally, we can compare this set of keywords, and we compare what we have in the system. And finally, we can find relations between request and the data. And finally, system can provide some smart, not smart, some answer. And it's something like up to some layers simply to polish this answer. But I think it's one of the possibilities, because currently what we do, we something like create file, provide name for this file. What is the name? It's Notion. What is a file? It's some byte stream, it's your value. So why system so lazy right now? Why system cannot do much smarter stuff? And it's not even not contradict to file system, because file system can do this even right now. It's complex, but it's possible to add. I consider for my file system. The problem here, you would like to have fast system. And if I will do this byte stream analyzing, it will be slow. I haven't something like enough computation power. And finally, again, if we adding more computation power, it's more power consumption. So this is a problem. So okay, we return to this problem that our hardware is power hungry. And first of all, we need to solve this because it's important. And we have spintronics that can help, but somehow we haven't commercialized solution. We are talking about photonic processors, I don't know, several decades. Where photonic processor? HP tried to deliver the machine. They tried to commercialize the machine in 2016. They failed because, first of all, they cannot deliver ReRAM. They cannot deliver photonic solution because they simply failed. And they didn't care about cache coherence. And this is a problem. If we would like to increase performance, we would like to add more cores. If we're adding more cores, we're adding cache coherence problem. And this is CXL that trying something like to say our memory is cache coherent. But CXL something like not so fast, something like around. If you add CXL memory model into your system, it will be maybe 100 nanosecond, maybe 200 nanosecond. If you're adding switch, every switch adds 100 nanoseconds. So, okay, I started to talk a lot about initial question. I think I answered on the initial question.
Yeah, thank you.
Any other questions? Because it's a big topic. It's a huge topic, and I can talk in different directions. I simply make really compact, something like description of the whole problem, because it's big, it's huge. And from my point of view, we didn't try to solve this. Because we're trying to polish something, not trying to solve the fundamental problem. And the problem here is that, okay, we have something like Linux kernel. We spent 20 years, or how many, from 1991, yeah? But before it was stuff like Unix and so on. It's a lot of money that we invested in the whole paradigm. We invested a lot of money into hardware. We invested a lot of money into software. Okay, I go to my boss and say, let's rewrite everything. So we need to spend how many years? Another 20, 50 years to achieve the same state of art? My hope, only quantum computing. This stuff can change everything because it cannot work on this hardware. That's all, only one hope. But currently only big toy, nothing more. Maybe somebody would like to suggest other solution. I'm ready to discuss. No? Okay. If no more question, so thank you for attendance.